Hi everybody, Dr. White here, continuing our discussion of bivariate distributions of continuous type. We want to look at the marginal distributions now. So definition for marginals for continuous is very similar to definition of marginals for discrete. You just integrate instead of sum. And so like the chance that capital X is just about equal to little x should be the sum of all of the chances for the different ways for f of x, y to be that given value. So you're adding up over all the different y's where this could happen. So nominally you're going, y goes from minus infinity to infinity. But when you actually get down to computing with your density function, you only need to go over the support, the possible values for the density function we were working with, when y goes from 0 to 2. And the formula for the density was this. So we just needed to do this little integral right here, which ain't hard. Turns out to be x over 2. And that's for all the x's in the support of bivariate random variable, so the x can go from 0 to 2. So a graph of that would be 0 for x's before 0, and then here's your x over 2 line, your y equals x over 2 line, and here is 0 again. And so areas underneath this density function would give you chances for capital X to be various things. Similarly, the marginal for y, you would just add up the chances, all the different ways that x can allow you to have that y. And x can again go from 0 to 2, got a slightly different definite integral to do. And so a different look to our marginal distribution for y. So there's its density function. It goes up to 1.5, which is what you get if you plug in 2 into here. Okay, how about expected values for your marginals? So one way in discrete world was to do sum over the entire sample space of, x times the PMF when we were in the discrete situation. Same here in continuous. If you want the expected value for the x marginal, you just integrate over the whole xy plane x times the joint density. Oops. Which of course means that you only got to run x goes from 0 to 2, y goes from 0 to 2 in our example, because f is 0 outside of that sample space. X times your PDF. And I see there's a typo. I left out a dx. Left out a dx right after the dy. Sorry about that. Might fix it, might not. I'm getting tired of constantly scanning in the PDF, fix typos. So you could do it that way. But hey, if you've already got your marginal, for a particular one of the variables, then you could just go the traditional way. Integral over all possible values, x times the marginal. So I'll just opt for that way this time, and it ends up being integral from 0 to 2, x times x over 2. And easy integral to do, and I get 4/3. You can also get variances for your marginal distributions, either the double integral way, or if you've got the marginal, the regular single integral way. Just make sure you're subtracting off inside of here the expected value for the random variable each time. So you have to get the expected value first before you head to any of these computations. So you can look at some examples of that in the textbook. Hey, in this example that we've been working with, are x and y independent? Let's check that out. So let's just multiply the marginal for x and the marginal for y together. Here's the marginal for x, and here's the marginal for y. Now that one's good for all x's from 0 to 2. This one's good for all y's from 0 to 2. So for everything in that square, 0, 2, cross 0, 2, for everything in that square, the product is going to be, let's see, 12 over 2 is a 6, xy squared over 32. So it'll be 6 over 32 xy squared. Now, the formula for the PDF was 3/16 xy squared on that sample, that space. And so, hey, 3/16 is 6 over 32. And so, all over S, the two are equal. And outside of it, you also have zeros for these two things, because f sub x, the support was just 0, 2. So it's 0 outside. Same here. And so this product would be 0, for any x or y that's outside the 0, 2 range. So truly, for all x's and y's in the entire R2 plane, this is equal to this. That's the definition of independence. So yeah, these two random variables are independent all along. So let's just compute a little bit with the expected values for conditional random variables here, just to see if everything matches up with our discovery that the two random variables are independent. So why don't we get the conditional distribution of capital Y given that capital X turns out to be some particular value little x. So what'll that be at various possible values of capital Y? Well, the definition for conditional distributions is going to be the same as it was with discrete type bivariates. It's the PDF over the marginal probability for the other variable. So f of xy over marginal for x. So this divided by the x over 2 that we found. Now that reduces to this, and that's good for all y's in the support. Once we've got the marginal PDF, we could go ahead and get the expected value of y given that capital X turns out to be little x. We just integrate over the possible values for capital y times that conditional PDF. And we work and we work and we get 3/2. So notice we get that regardless of what x is. There's no dependence on x in the answer here. That tells me kind of in advance that we're going to get the same thing if we just asked for the expected value of y knowing nothing about x. Let's check. Integrate over possible values of y times the marginal for y that we found up here. And so when we do it, we get to this spot right here, and we look at it and we say, hey, wait a minute, we were just doing that. We're going to come to the same thing. We're going to come to 3/2 again. And so knowing what capital X turns out to be does not change what you expect capital Y to be. It's going to be 3/2 still. So that's another confirmation that these two random variables really were independent.